There is an algorithm or there is a package available within R which will also help you determine the K value, which is K selection. If I install and run this package K selection, oh, there is an error. Probably I will have to install this. Just bear with me, it might take just less than 5 seconds or so. Yep. Let me press that key to get this. Wow, library is loaded. Now if I run this K selection on a dataset called Iris dataset, if you're wondering on what that Iris dataset is, question mark of Iris, we have this Iris dataset which gives the measurements in centimeters of the variables such as sepal length, sepal width, petal length, and petal width. For 50 flowers, and you have 3 species, Setosa, versicolor, and virginica. Right? And when you look at that Iris dataset, right? So let me run it here. View of Iris. Here is the Iris dataset. And I do not want to include probably this 5th column, which has the cluster names, right? So it has a species name. Ideally, you'll not know that. You'll be given sepal length, width, petal length, and petal width, and you need to cluster them together. So I want all the rows and I want to exclude the 5th column. Parallel equal to true, and K underscore threshold is 0.9, maximum centers is 12. Let me explain this to y'all. First, let me run this. Now it says no parallel backend registered. So there's no parallel processing possible. That is what it says. Now if you do question mark of K selection, you can understand on what is K underscore threshold value. Maximum value of function of K from which cannot be considered the existence of more than one cluster in the dataset. Right? The default value is set at 0.85. You can do some more research on that. There's an additional clustering technique that I'm exposing you all to. You can do additional research. Maximum number of clusters that you want to use for evaluation is 12. Like within sum of square, here we have chosen 8 maximum clusters. Here we're choosing 12. Right? And f of k value is calculated using a different evaluation altogether. Look at this. So in this method, a function f of k is used to evaluate the quality of the resulting cluster and help decide on the optimal value of k for each dataset. And this is your function of k. So you can probably spend some time looking into the algorithm behind the scenes and get a sense of that. So this is how you determine the k value. Now if I just run k, finds 2 clusters. So it's saying that 2 is the number of clusters that I would suggest. But here it says no parallel backend registered. And your algorithm was executed sequentially. If you execute it sequentially on a large data set, it might take a lot of time. Hence, we might want to probably use this do parallel. Yep. And you know, it depends on how many cores you have. On my computer, if I go to about this Mac and try to look into system report, it would say that I have total number of cores too. So people, if you want to work on data science, on parallel processing and big data sets, 4 to 8 cores is what I would recommend. Your server configuration would be probably 32 cores, etc. So your parallel processing will be so much more faster on your servers. So I have only 2 cores, so I cannot say I will be assigning 4 cores. I need to assign both of these cores. Right? If there are 2 applications running, one application might run on 1 core, another application might run on another core. CPU, right? CPU cores is what I'm speaking about here. Now if I register parallel and say there are 2 cores, and if I now run this case selection, it has not given me this warning message which says no parallel backend registered. And if you run this on a large data set, all right, here also it says 2 clusters. When you run it on a larger data set, you would appreciate this completely. and it'll be much faster if you use the package do parallel processing basically. And if you are using, say, and yeah, parallel processing is one thing. And if you have a large data set that you're dealing with, you can also probably use Clara, clustering large applications. Right, cluster is the function package. Okay, I've loaded that. I'm doing a row bind. First of all, within that, I'm creating a column bind using normal distribution. I'm randomly trying to generate 5,000 data points with mean 0 and standard deviation 8, and I want to come up with another set of same 5,000 random values from normal distribution with mean 0 and standard deviation 8, and that's column bind. I'm binding these two, and I'm generating another set of random numbers from normal distribution, 5,000 of those with mean 50 and standard deviation 8. I'm generating another 5,000 entries randomly using normal distribution with mean 50 and standard deviation 8. And when I generate all these, I'm doing an R bind, row bind. So we'll look at the output final out. There we go here. So now I think it makes sense, right? So we have randomly, if you look at this, we have 10,000 entries. So we have generated 5,000 entries for V1 and another 5,000 entries for V1, and we have combined those two using column bind, and we have generated another 5,000 entries with different mean and another 5,000 entries, and we have done a column bind, so one beside another, and then you're combining these two into this row. So if you want me to explain that, this is how it is. So you randomly generate 5,000 entries. If I take an average of the entries, it'll be 0 and standard deviation will be 8. Another set of 5,000 entries are generated using this function, and these two are combined using column bind. And now you are generating another data set altogether. So you're trying to generate 50 random numbers, 5,000 random numbers. And if you take an average of all these numbers, it turns out to be 50, and standard deviation of this data set would be 8, right? And you're again generating 5,000 numbers randomly from normal distribution. Here, and you're combining these two using column bind. So I have two different data sets now, right? Kind of, this is one data set, this is another data set, A and B, with different mean and different different means. So why did I do in that way? Because when I do this clustering, I want the model to say that this is one cluster and this is another cluster, just to show you on how the algorithm works. Now what am I doing? I'm doing a row bind. So I'm binding these two, and this B will come and sit. Let me choose a different color. This B would get appended here towards the bottom because it's row. I'm binding using row, not by column but by row. All right, and I just want to show you this. That's the reason why we are running that way. So we are running Clara on this data set. Clara is clustering large applications, and we are saying that we want 2 clusters, right? And we are just considering a sample of 100. Let me run that. There we go. And if you do a class plotting this cluster, you'll be able to see those. There we go. It is saying that this is one cluster and there's another cluster. In from this data set, randomly 100 data points are selected, sample. You have not chosen everything in that sense. Now, there is something called as PAMS, also partitioning around medioids. I'll show you on what medioids is in just a moment. So I'm running the PAM algorithm on this data set, and I'm saying 2 clusters. So look at how much time it's taking, and do you know how much time Clara has taken? Split second. right? I just want to show you the difference between these two. And if you do class plot, it will also more or less give you a similar kind of picture. This is cluster 1, this is cluster 2. Yep. And the difference between median and medoids is, yep, I'll try to explain that using your internet. If you look at this explanation of medoids, medoids are similar to mean or centroids that we have discussed, but in a cluster using all the different data points, you tend to calculate the centroid, but when it comes to medoids, it is always a member of the data set. A member of the data set would be called as a medoid. And medoids are most commonly used on data when a mean or centroid cannot be defined using a 3D trajectories. Yeah, that is when you end up using that. Right? Common application is k-medoids clustering, and you use it when k-means algorithm, it's similar to k-means algorithm, but works when a mean or centroid is not definable, and that is when you do this. Yep. All right. Now I think I will have to explain you all about a case study that I was part of, just to give you all a sense on what kind of analysis you need to do. Right? Just give me a moment.